One last point about heat engines. One particular type of heat engine is called a Carnot engine, which goes through something called the Carnot Cycle. So again, we're starting out with some hot substance, using that to transfer heat into our system, and then out of our system we get work, and we get heat going into our cooler substance. The Carnot cycle is a specific way to do that. It's a four-step process. So we have two expansions first, so our piston gets further and further out in these two steps, and then two compressions, and our piston gets further and further in, or our gas gets more and more compressed during these two steps. And it's been calculated that the Carnot cycle it's just a really efficient way to do a heat engine, to do this process. In fact, as far as we can tell mathematically, this Carnot cycle, if we could get it to work exactly, would be the most efficient that an engine can be. So we start out with isothermal expansion. So these black lines, those are isotherms. They're just curves of constant temperature. So isothermal expansion from some point here down to this point. So we're getting larger in volume. Our pressure is decreasing at this point. Then adiabatic expansion, and in this step we have no heat transferred to the outside, and it's the adiabatic steps here that are problematic for us because we end up transferring quite a bit of heat to the outside. It's really warm gas inside these pistons, so a lot of heat gets transferred. So these steps we don't do as well as we would like to. In real engines. But anyway, we have isothermal expansion, then adiabatic expansion, then isothermal compression, and then adiabatic compression. And so it's useful to figure out, if we look at these temperatures for each of these isotherms, how does that impact the amount of energy that goes into the system, the amount of heat into the system, and how does that affect the amount of heat coming out of the system? So if we think about the equation delta U is equal to Q plus W, where Q is the heat going into the system and W is the work done on the system. During that isothermal expansion, isothermal means temperature doesn't change, so this is for the first one. So delta U is going to be 0. The temperature doesn't change, so internal energy doesn't change. Is going to be equal to Q plus W, or we could say that Q is equal to negative W, the amount of heat going in at this hotter temperature. So I'm going to look at, call that QH, and this is WH. And so if we wanted to know how much work was being done by this gas as it expands going along this path, well, we could do that just by taking the area underneath this curve. So we look at this area right here. Okay, and we see that that area would get larger with larger expansions, of course, with a bigger width of this shape, or it would get larger if our temperature of the hot part of this cycle was higher up. So from this we can learn that as TH increases, QH increases as well. Okay, so if we have really, 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 really hot gases inside there, then a lot of heat gets transferred into our system, into our expanding gases during this. Makes sense. So now if we go a little bit further, we have this adiabatic expansion, and in adiabatic expansion we know that Q is just 0, so we don't need to worry about how much heat is going into the system at that part. It's none at that point. Then we have this isothermal compression. So for moment 2, or for process 2, Q is equal to 0. And then for process 3, again we have delta U is equal to Q plus W, and delta U is 0 because it's another isothermal process, is equal to Q plus W. And so we see that Q is equal to negative W again. And this time we're talking about at the cold temperature, QC, and work C. And so now we're looking at, new color, purple will do. Now we're looking at the area underneath this curve. So that'd be this little area right here. And again, we see that if TC were larger, if our isotherm were higher up here, then this purple area underneath, that would be larger, and so the work would be a bigger amount, and so the amount of heat that's leaving this system now would be a bigger amount as well. So from this we get, as TC increases, then QC increases as well. So our goal in these engines, the idea is that we want to maximize QH and we want to minimize QC. So to make this this engine generate as much work as possible, we need a really, really hot temperature, and we need a really, really, really cold temperature. And remember, the closer this gets to absolute zero, the more efficient our machine becomes as well. So with these two findings, we can think about what would be necessary to have really powerful, really efficient motors. And it's just that we have to have one really hot side and one really cold side. That's all there is to it. Now, with engines operating in the air that's at a temperature that human beings can survive at, we're really limited in terms of this TC part of the equation.